So our first speaker, I don't know much about him. We just found him somewhere. I heard he was nice. So I hope you enjoy. We're up. Okay. Oops, sorry. This is the wrong time. Hello. So I'm going to talk to you about how methods are formed today. This is the title of my talk, but I also like to call it Method Mania, my other talk title for it. I'm super excited to be here at RubyConf Philippines. This is my first time in the Philippines, so this is really, really great. It's been so awesome to look around and see different stuff. Although one thing I noticed that was kind of strange is that apparently this conference uses PHP for all of its payment processing. So I thought it was kind of weird, like maybe we should be using Ruby instead. I also thought it was weird that all the ATMs distributed PHP. That was, I don't know about that. So like I said, this is my very first time. This is my very first time in Manila, and I was really excited to come here because, you may not know this, in the United States we have these folders called Manila folders. You probably just call them folders here, but we call them Manila folders. So I was really excited to see the birthplace of Manila folders. Now, many of you may not know this, but apparently when the country was founded by Alexander Manila back in the 1800s, these folders actually grew on trees like this. So they would grow here, and people would harvest all the folders off of the trees. Now, unfortunately, oh wow, that's a slow transition, sorry. Unfortunately, due to overforesting, like people harvesting these way too much, all the Manila folder trees have died off. So unfortunately, you can't get natural Manila folders anymore. Although we went around the city yesterday, and I actually was able to find a place that sells all natural Manila folders. So that was, I took a picture of that. So the other thing is that I also wanted to share with you, like I had to prepare this presentation, and I had a lot of files for doing that, so I kept it in a Manila folder on my desktop. Sorry. The other thing I want to point out is that since I am the first speaker, I get to use all of the good puns. You can probably see all the other speakers in the audience now deleting all of those PHP puns from their slides. Anyway, my name is Patterson. You might know me on the internet as Tender Love. That was my photo right there. That is me, and that is my Twitter address, so you can find me online. I now work for GitHub. This is my company. This is the first conference where I get to say I work for GitHub. Today is I've completed my second week working there, so I've been working there for 2 weeks. And you can tell from the slides I'm not super good at branding. See, there's another slide with our brand. Anyway, so I work for GitHub. Buy our products, please. I love cats. I really, really love cats. I'm going to show off some of my cats. This is one of my cats. Her name is SeaTac Airport, Facebook, YouTube, but we call her Choo-Choo for short. This is her. She likes to sit at my desk. And I don't know if you know this, but we have a presidential election going in the US right now. So I tried to dress up my cat to look like him. That's kind of see, she's got the same hair. This is my other cat. He's a bit more famous. This is Gorbachev Puff Puff Thunderhorse. And unfortunately, I didn't bring any GitHub stickers today, but I do have stickers of my cat. So if you want a sticker of my cat, please come say hello to me. Also, my wife made this slide. She wants me to do a TED Talk, so I just use this slide. There's really no reason for this. It's just here. And also, I enjoy hugs, so please come give me a hug later. So today we're going to talk about methods. We're going to talk about methods and method optimizations. We're going to talk about, different types of methods, how methods work, bytecode, VM internals, and then we're also going to look at some method optimizations, including inline caches, polymorphic methods, polymorphic inline caches, and optimization tests. And really what I want to say here is that I have organized these slides very carefully, and I want you to know that there is a method to my madness. I'll be here all day. All right, so this talk is highly technical, but I want to give some advice for new people out there. I've tried to make this talk as accessible as possible, but I'm going to be covering some pretty technical stuff. So I'm going to start out with some high-level stuff and then dive into deep internals. But if you have questions about this stuff, don't be embarrassed to ask me. Like, I didn't know this. There's a point in my life where I didn't know this stuff. So please ask me questions about it. Yes, so please ask me questions if you don't know this stuff. I would be happy to talk about it. So we're going to start out with some high-level stuff and then go into low-level details. And the way this talk is kind of organized is that we're going to learn some stuff, and then we're going to fail. I will show you how I applied this learning and then failed, and then maybe do some successful things. But what I want you to know is that you should probably just lower your expectations about this presentation. So, all right, let's get started. First, I want to talk about call sites. What exactly are call sites? So here's an example of some Ruby code. If you look at this Ruby code, we have an example of a call site here. Pretty much any place with a dot is what we would call a call site. That's where a method gets called on something. And just so we have a little bit of terminology, I might say something like left-hand side and right-hand side, and what I'm referring to is the left-hand side of the code, so that is the left-hand side, that hello variable, and the right-hand side is the method name, so we have the left and the right-hand side of our call site. And I want to show a few more examples of call sites in some code. So we have just some example code here. We got a dot here, we got a call site there. Down where we call object.new, there's another call site. That one's against a constant and a method name. We have another call site here where we're calling just foo. And you'll notice we don't have a left-hand side there. It's actually an implicit left-hand side, which is self. So self is main in this case. If you write a quick little script and you just say put self, you'll see it says main at that point. Another place here, we have another call site here, which is interesting. You can think about case when statements as translating to object triple equals X. So we have a call site there as well. One here with the double equals, another here with the print statement as well. So there's call sites all over this code when you're looking at it. So now that we know we have where call sites are generally located when we're looking at code, we can kind of see where those things are. Now, from there, I want to take a look at how to understand how Ruby's VM works. Now, Ruby's VM works very similar to a calculator. MRI's VM is stack-based. And the way stack-based VM works is that we have a stack of instructions, or we have a list of instructions, and that manipulates a stack. So the way this might work is we say, okay, we're going to push the number 6. That 6 gets pushed onto the stack. Then we push an 8, that also gets pushed onto the stack, and we say add those, and it pops those two values off the stack, and then puts the value 14 back on the stack. So our bytecode might look something like this. We can think of our bytecode as an array of arrays, so where we have one giant array that's all of our bytecode, and then each element of that array is the instructions along with operands for those. So the point I want to make with this slide is that bytecode is actually there in memory. It's something, it's there, and we can actually manipulate it. It's a thing. It's there. And if we break down this bytecode, you can see on the left-hand side we have an operator saying push, and for the operator we have an operand. So that's kind of a high-level overview of how the virtual machine works. So how do methods actually work? At a high level, what the VM does is it finds the name of the method, then it finds the type of the left-hand side, then it finds the method given the above information. Then it actually executes the method. So at a low level, if we want to look at how this actually works in detail, we can take a look at the bytecode that's generated. So for example, we have this method here, foo, And if we use this Ruby VM instruction sequence code at the bottom, we can actually view the instruction sequences for this method. So we can see the bytecode. If we run this code, it prints out something that looks like this. I know it's not too readable, but that's okay. We really just want to look at the structure of this. You'll see right here, these two particular lines are pointing out that bit of the bytecode. And if we change the method to have 2 method calls, we change that foo method to have 2 method calls, and print out the bytecode again, you can see it looks like this. And we essentially just repeated those 2 lines. You can see we're repeating those lines. And we can map this bytecode back to the original code somewhat like this. So we say, okay, we've got our original code there. This first operation, it gets the value from the parameter. Then the second operation actually maps to the method call itself. So that first operation pushes that value into the stack. The second operation actually calls the method. So if we look at the bytecode too, we can see we have an operator and an operand. That's saying what position we want to get, what parameter position we want to get, and we have another operator and operand below that's saying, okay, this is our bytecode for calling the method, this is the method that we actually want to call. And this one that actually calls the method, we have a third parameter here called call cache, which I'm going to talk a little bit about later, but for now we're just going to say it's a thing there. We'll cover it in more detail later. So if we look at how this actually works, what happens is it'll say, okay, we have a stack and we have our method calls. The first thing that happens is this get local, gets that local variable, puts it onto the stack, and then the second instruction sequence actually calls that method. So come on, transition, go. There we go. So it calls the method, and the way this actually works is it says, okay, grab bar off the stack, pop that off the stack, called baz, and then push the return value back onto the stack. So at the very bottom we have, when that bytecode finishes executing, we'll have a value put back on the stack. And if you look at Ruby's source code, you'll find a file called imsns.def, and that's where all the bytecode for Ruby's virtual machine lives. So if you want to start understanding how the virtual machine works, just go pop that file open. You'll see this is an example of one of the bytecodes. You don't really need to know C to read this. It's kind of, if you just read the words, you kind of get an understanding of what's going on. So this is the name of the bytecode right there. Below that is the parameters for the bytecode, and you can see down here it's actually calling VM search method. So you can see, yes, it's searching for a method. Then we actually call the method, and then it pushes the return value onto the stack. So how do we actually find that method? It said we had that function VM search method, but how do we actually find that method? The way it's found is it looks something like this. I've taken the C code and translated it into Ruby, so it's a bit easier to understand. But essentially what we're doing is looking up a method table on the class and looking for the method on that method table. And if it doesn't exist, then we try the superclass, et cetera, until we actually find it. So for example, let's say we have some code that looks like this. D at the very top has the method, and then we have B, C, or C, B, and A that inherit. So the way that this code will actually work is we have a hierarchy that looks like this. The first thing it does is say, okay, well, do you have foo on A? It looks up the method table for A. A doesn't have it, so it tries the next one, looks at B. B doesn't have it, so it tries C. C doesn't have it, so it tries D. And then finally it finds the actual method, and we can call it. So if you think about this operation, we can say that method lookup is an ON operation, or a linear operation, where N is the number of ancestors a particular class has. So what this means is that the more ancestors some particular class has, the slower a method is going to take. It'll take a bit longer to actually find that method because it has to go up more and more. So we can actually test this out. So I wrote some code to test out method speed. And you don't really need to read this too closely, but essentially what it does is it says, okay, we're going to set up a class with 10 ancestors. We're going to set up another class with 10,000 ancestors, and then we're going to see which one is slower to call a method against. And you'll notice here that number is not actually 10K. It's because there's some other classes, but it's close enough, right? So if we run a benchmark against this, and we're measuring iterations per second, so iterations per second means that the higher the number is, the faster it is, you'll see that the result is essentially the same. It doesn't matter whether we have 10 ancestors or 10,000 ancestors. it's nearly identical. So what is actually going on? Why are these the same? We know from that logic before that the one with more ancestors should have been slower. So what's the deal? Well, this is how we can lead into talking about speeding up method calls. One technique for speeding something up is, we all know this from our application development, is that if we have some calculation that never changes, we can just cache that calculation. There's no reason to calculate it over and over again. We don't never change it, so we'll do it once and store it in a cache. So if we take a look at this benchmark, we'll see that, well, the ancestors of 10 and the ancestors of 10,000 never change. So if we know that those ancestors never change, then why do we need to look up that method? Why do we need to go through that hierarchy every single time we call the method? So if we take a look at the bytecode for this benchmark, you'll see in one place we have that op send without block, and the call cache is where we actually cache that method lookup. So we say, all right, we're going to look up that method and we're going to cache it someplace, and the place that we cache it is actually in the bytecode itself. So we can say that we cache this value in line with the bytecode. So the cache is in line with the bytecode. In other words, we can call this an inline cache. So if you hear people saying, oh, this code breaks method cache, this is what they're talking about, is this particular cache where somehow doing some code that makes it so that cache doesn't work. Like we've changed it such that we can't look up the value from there. So we're going to talk a little bit more about breaking method cache in a minute. But again, back to our example of this code with all the different call sites. Here is where all these call sites are in this code. Now, this one here with this when statement is slightly different. I've highlighted it a little bit differently, and I want to take a slight detour about this particular bit of code because I think it's interesting. So this is a very slight detour about case when versus an if statement. So let's take a look at this example code here. You'll see we have one method that uses an if statement with a bunch of triple equals, and then one method that uses a case statement, and then we have a benchmark that compares the two. So these should be equivalent methods. They should do exactly the same thing because we know that the case statement translates to triple equals. But if we run this benchmark, you'll see that the case when statement is actually slightly slower than the if-else counterpart. So why is that? The interesting thing is that this call site with the triple equals actually has a cache. We cache the lookup of the triple equals, but there is no cache with the case when statement. Don't go changing all of your code. We can fix this. Okay? It's fine. Don't go changing your code. Leave your code. It's fine. I just thought it was an interesting fact to bring up. And you can verify this if we dump the bytecode for each of these methods. You can actually see it. So this is a comparison of the two. You'll see the if-else statement has a call cache on it where we're actually caching that method lookup, and the case when statement does not. It doesn't exist there. So again, don't change your code. Don't change your code. We can fix it. It's okay. We'll just put a call cache in that other place. It's just a little bit of work. Don't worry. The other thing I want to bring up is that if you look at all these caches are everywhere. They're everywhere in your code. So when we're thinking about these call caches, if we want to improve these cache sites, the size of those caches actually matters. If we were to double the amount of memory that call cache would use, then imagine the impact on your code if they're so prolific through your code base. Okay. Anyway. Moving on, we've studied where this cache is. We know where it is, right? And you probably know you're using, like, I don't know, Redis or Memcache at work in your applications, but if you're using some sort of cache, you have to have a key and a value pair typically, right? So we know where this cache is stored, but how is it actually keyed? What is the key and what is the value of this cache? So we have this one call site. And the call site here, the key of it is actually a serial number, and that serial number is stored on the class of that object. And the value of the cache is actually the method. So we get the serial number of the class, that's the key, and then the value is the method that we actually looked up. So this class of method returns the very first ancestor of the object, and that's going to be a little bit more interesting later. So let's look at how to make cache misses. So how can we make it miss the cache? Now, the way that you can tell if it's missing is there's a method called rubyvm.stat, and this is completely specific to MRI. Don't try to use this on JRuby or anything. If you're using MRI, this is what you can look at. If you look at these values, you'll see a hash that's printed out, and these are internal values of the Ruby virtual machine. If that global method state changes, that's very, very bad. And I've shortened up vary to V because I've noticed that the younger generation is shortening words that don't need to be shortened. So I'm trying to be relatable. If that global method state changes, that's very bad because it means it expires the cache for everything in your system. All caches get expired, so you don't want that number to change. If the class serial number changes, that's not very good. It's not good, but it's not the end of the world. You don't want it to change. Ideally, this number will what do you call it? It'll stop changing eventually. You'll actually see this number change during startup of your application, but it should stop changing eventually at runtime. Now, I wanted to show an example of this this cache actually breaking. So I just decided to try printing out these values with RSpec. So if you write an RSpec test that looks like this, just print out rubyvm.stat and run this test. If you look at the output, you'll see that the output looks like this, and that the class serial number is changing between every single call to it. So what this means is that RSpec is doing something at runtime that's breaking method caches. Now, if you're using RSpec, don't freak out and change all of your tests to mini-test, although I personally use mini-test, so maybe you should. We can fix this in RSpec, and I've already opened a ticket for fixing this, so don't worry about it too much. We can deal with it, but I just wanted to show you what it looks like at runtime, so you can actually see something changing. Now, ways that the cache is actually broken are, this is an example. Every time you define a new module, you'll see that the class serial number changes. Every time that you define a new class, you'll see that the serial number changes. Every time you add a new method, you'll see that the number changes. So you'll notice that this number changes a lot at boot time, but should stabilize when your application is actually running. Now, another way that we can do this I like to think of this as like maybe boot time or compile time cache breakage, something we don't really need to worry about. The ones we really need to worry about are runtime breakage. So I put together a little bit of code that tries to show you runtime breakage, examples of breaking at runtime. So this method on the left here, all it does is print out a difference between those two, or between the stat before and after, so you can see what the changes look like. Now, if you extend an instance with a module, that'll break the cache. If you do an instance exec, that'll break the cache. If you access the Singleton class, that will break the cache. So anything that you do at runtime that accesses the Singleton class of an instance will break your method cache. So the reason that this happens is because when Ruby is looking up the class, the serial number for the class of that instance, it has to look at either the real class, the very first ancestor of that instance. So for example, it's kind of hard to read, but this instance exec, when you do that instance exec, it actually creates a Singleton class, and that's the very top there, or the very closest to your object. So you know that A was an instance of foo, but as soon as we did instance exec, or accessed that instance object, or that Singleton object, now it's actually an instance of a Singleton class that inherits from foo. So B actually, this bottom one, B, it inherits from foo, where A inherits from an anonymous class that inherits from foo. So when we access the class of is going to return either the Singleton or the actual class. And if you look in Ruby's source code, you'll see that this is referred to as the real class. So the real class is either the Singleton or it's the actual class itself. All right, so cache misses. We've seen two types of cache misses. Typically when we're creating new classes or new modules, which is done at boot, or when we're accessing a Singleton class. This is usually done at runtime. There's another one that's a bit more, well, I don't know if it's important. You'll see why I'm saying that later. Another one that's kind of interesting, which is polymorphism. So polymorphism, writing polymorphic code can also cause these cache misses, and I'll show you why here. So for example, we have two examples here. On the left, we have one bit of code that's not using polymorphism, and on the right, we have another bit of code that is using polymorphism, and they're calling exactly the same number of methods. So it's doing the same number of method calls, just one is polymorphic and one is not. Okay? If we run these two tests, you'll see that the non-polymorphic one is much faster than the polymorphic one. The polymorphic one takes about 400 milliseconds more than the non-polymorphic one. So, even though they're calling the same number of methods. So why is that? The reason is because if we take a look at this call site here inside of the foo method, you'll notice that this class of is going to alternate. It's going to be of type A or type B. It's going to be type A, type B, type A, type B, alternating between A and B and asking for the serial number between those two classes, which means we're always going to miss. Since the serial number is always changing, we can't look that method up in the cache, and it misses that cache every single time. This cache never hits, which is why one is slower than the other. So we can say that on the left-hand side, this call site always sees type A. We say that it sees type A, where the one on the right, it sees type A and type B. We have two types there at that particular call site. So the thing that we can call this is call sites with one type, we can refer to those as monomorphic. It means they see one type. Okay? When we see two types or more, we can call those polymorphic sites. Now, if there's too many types, we can call that megamorphic. And too many, I'm putting that in quotes, because what does too many mean, right? How many is too many? We'll talk about what how many is too many means in a bit, but too many means megamorphic. So these are some vocabulary words you might need to know. So how do we speed this up? Today, if you look at the way the cache is accessed, you'll see, okay, I've translated this into Ruby. We say, give me the class of something, of the variable. If the serial number of the class is the same as the serial number in the cache, then we have a cache hit. And we don't need to look up the method, we can just get it from the cache. If the serial number misses, then we're going to set a new cache. We say, okay, we'll set the serial number to the current serial number, and then we'll go find the method and return that method. So we can say today that Ruby MRI has a monomorphic inline cache. This cache is in, let's break down these words. It's monomorphic because it caches one thing. It's inline because it's in line with the bytecode, and it's a cache because it's a cache. What I think would be nice is, well, what if we were to cache multiple values? Let's say we cache 2 instead, right? We could say, well, instead of having one thing in this cache, maybe we cache a few. We have a list, maybe a short list, and we say, well, is anything in this list matching up with the thing that we're looking at today? If it does, let's say we have 2 in there. If it does hit, then we don't have to look up the method. So this is where the term megamorphic comes in, as we say, well, 2 sites, we're okay caching 2 values, but maybe that particular call site sees 3 or 5 or 1,000. That's too many for our cache. And we can use different optimization techniques at that particular site. But in this case, we want to have a polymorphic cache. We say we cache multiple values. So this can be referred to as a polymorphic inline cache. We're caching multiple values, so it's polymorphic. It's inline because we're storing it inline with the bytecode, and again, it's a cache because it's a cache. So I wrote a patch to actually do this with MRI. This is what the patch looks like. I want you to read it very carefully because there's going to be a test later. So that's what the patch looks like. It's a little bit long. No, it's okay. Actually, it's not too bad. It's 186 line diff, right? So not too bad, and that that's all white space and whatnot. Plus it's C code, so 180. Come on, not bad. All right, so let's go back to that previous benchmark that we had. Test A and B. We had a monomorphic version on the left-hand side, monomorphic, and polymorphic on the right-hand side. Now, if we run this test again with that patch applied, you'll see that the times are almost exactly the same. So the monomorphic version is the same speed as the polymorphic version. We've sped up the polymorphic version. So this is great. Mission accomplished. We win. Yes. Now, unfortunately, if you improve the speed, unfortunately, we need to figure out whether or not this actually matters. So we've sped up this particular test case, right? We made these polymorphic methods just as fast as the monomorphic methods. That's great, but does it actually matter in our application? So I was really excited to write this polymorphic inline cache. I wrote it all, and I was so happy. The two benchmarks were exactly the same speed, and I'm like, yes, I did it. I did it. It's the same speed. Let's apply this into Ruby, and we're done, and everybody will be happy. But then I thought, does this actually impact our application? So one performance tip that I want to give all of you is that you should only speed up bottlenecks. So the thing about bottlenecks is you need to measure your code to find the bottlenecks first. So if you don't know where the bottlenecks are, then you can't really speed up your code. So how do we know if polymorphic call sites are actually a bottleneck in our code? Well, we need to measure what percentage of the call sites in our code are actually polymorphic. How can we do this? How can we measure this? There's no way to do this in MRI. So what I did was I added logging to actually look at the point where we look up from that cache. So we'll say, all right, every time we try to look up a value, let's log that, and let's also log whether or not it was a hit or a miss, right? And this is the patch where, again, I'm going to test you on this later, but this is actually much shorter. And what this let me do is let me say, okay, I'm going to register a trace point, and this trace point will execute anytime there is a cache hit or a cache miss. And inside this block, what it does is it prints out the call site information. And I care about cache hits and cache misses. I want to get notified on both of those events. And right here, I actually enable that. I enable that trace point. And you'll notice after I enable it, there's actually two call sites. There's one here at the very bottom where we call o.foo, and there's another one up here where inside the foo method it calls bar.baz. So we'll expect to see two events hit from that trace point. And you'll see that when we run this code, that's actually what happens. And the value that it prints out is the call site ID. This is a unique ID for that particular call site because we need to be able to identify all the different call sites in our code. The serial number, that's the serial number of the class. Now, we know that the serial number is important because it's our cache key, but for us humans, we don't understand what that serial number is. It's not very meaningful to us except that it's the key. So I also printed out the name of the class so I could kind of get an idea of what was happening there. So if we run this against more method calls, let's say we have a bunch of code and we want to figure out what percentage of the call sites in this code are polymorphic, we can just execute. This is the actual test on the left-hand side. I kind of blew up the important code on the right-hand side. But you'll see, we have some code here with some of them are polymorphic call sites and some of them are not, and we just log all of those. And once we've logged all of those, we can put together a graph of what percentage are polymorphic and what percentage are monomorphic. So after running this, if we look at the logs, we'll see that okay, three of these call sites were monomorphic. And one of the call sites, is it one or two? One of the call sites is polymorphic. So about 25% of the call sites in that example code are polymorphic. So I needed to test this against an application and try to figure out what percentage of the call sites in our application were actually polymorphic. So I ran that against this code, which is the place where I used to work 3 weeks ago. And it's an open source Rails application, so it's important to me to use an open source application because then any of you can actually try it out, but I'm also going to be testing this at work as well. So I logged about 4 million method calls. So all I did was I booted up the application in production mode, and then I also loaded the database with some production data, and then clicked around on the website to try and reproduce what it would be like actually in production. Now, unfortunately, there is some very, very bad news, extremely bad news. And you will see the bad news in the form of this graph. Now, what this graph is along the x-axis, that is the number of types seen at each call site. And the y-axis is the number of call sites with that many types. So this very left-hand side means that we have, where it says 1, that means it's a monomorphic call site, and the or the y-axis is the number of call sites that are monomorphic. So what this means is that a polymorphic inline cache is only going to target that bar. That is all that it will optimize. That's the only thing that it will optimize, and that's a very tiny percentage of all the method calls in the application. So what this says is that most call sites are actually monomorphic. It means that most of them only have one type. So caching 2 types may not help so much. So let's look at some hopefully interesting stuff that we learned from this. One is that if you look over here, we have a call site that sees over 16,000 types. So it sees 16,000 different types. Now, I tracked down exactly what that was, and what it is it actually came from EventMachine. At the time, we were using Thin as our web server, and Thin uses EventMachine. And if you look at in the EventMachine internals, you'll see that it uses instance eval, which we have learned instance eval creates a Singleton class and will break our cache. So, oops. Every EventMachine connection will not be cached. Now, the other thing I did is I broke it down and looked at just call sites where the number of types is 2. What do those call sites look like? What values do we actually see there? And this is what the breakdown looked like there, and I know you can't read the bottom. I tried to make it a little bit more readable in Keynote, and it really didn't help. So let's just look at the very top one. The very top one, we would see set and array. So at this call site, we would always see either a set or an array, and the actual code was set or array.include. So sometimes set or array was a set object, sometimes it was an array object, and it was just calling include question mark. Now the interesting thing is, I tracked down the points where it was an array, and there's no reason for it to be an array. It could have been a set. So we could just change the code to be a set, and now this place is actually monomorphic, and the cache will always hit. The next one was array or nil. And all it was doing was calling array or something.blank. So I was trying to check to see whether or not that thing was blank. And I tracked down where the nil came from, and it turns out it didn't need to be nil. It could have been an empty array. So if we change that nil to an array, now it's also a monomorphic site, and it's hitting the cache. And the next one was symbol or string. That one's a little bit harder to change. But what's interesting is that these particular places, they're accidental. I want to call it accidental polymorphism. It wasn't done on purpose. It just happened to be an array, or it happened to be nil. But it very well could have been a set. We could have made it monomorphic. These are what I like to call accidental polymorphism. Very few of these polymorphic call sites were actually done for performance or behavior-related reasons. For example, maybe we have some code that looks like this. This is an example of a performance-related polymorphic site. Where the left-hand side, we're always doing this thing double equals some other value. Well, if we know that we're always doing that, we can actually use polymorphism to do that test once, and then generate two instances, one that each of them, they don't have to do that test every single time. Or maybe we want to change behavior, so we would configure an object with some configuration object. So both of these examples are like purposeful polymorphism. So something to take away from this are that Pixar polymorphic inline caches are load specific, so it really depends on what type of code you're running. So this particular application didn't mostly use monomorphic call sites, and that might not be true for all applications out in the world. So if you can, I would like you to test this code with your application and see what this graph looked like, and you can actually get all the code that I was showing from these 2 branches on my GitHub page. So one thing I want to say is that it's only a failure if you learn nothing. So I found that these particular places didn't, we don't really use polymorphic call sites, so this particular optimization isn't really going to help us out. But I did learn some stuff, especially about our application and inline caches. So I decided to try doing something that didn't fail. I like to do stuff that doesn't fail once in a while. So what I wanted to do is look at how we could speed up singleton access. What's interesting is if we looked at those previous cases where we're accessing the singleton, it didn't really add any methods, it didn't change the object, so why are these slower? And I thought to myself, well, okay, we know that this particular case we're accessing the singleton serial number, and the other case we're accessing the real class's serial number. But if you look at this code, for example here, at foo.new, at that particular location, this is what the ancestors look like. It's foo and object and kernel. And then as soon as we access the singleton class, Ruby automatically, behind the scenes, creates this singleton object for us. Now, the class changes, so the serial number also changes, right? Our ancestors change, so the serial number also changes. And these serial numbers are used for method table caches, as we saw earlier. And what's interesting is if we take a look at this class serial number as we're changing the shape, you'll see that Ruby detects every single time we add a new method, right? It knows this serial number increases every time a new method is added. So Ruby knows when methods are added. So if we think about that fact, we take that fact into account and we look at this code again, we'll notice that we're not adding any methods to this. No methods are getting added. So, what's the point of the serial number changing? Why does it need to change? So I put together a benchmark test, and if you look at this benchmark, what I do is I create a whole bunch of objects where we access the singleton class. And then just iterate over it, and you'll see right here, this is the call site where the inline cache would miss, because every single one of these objects has a different serial number. So what I decided to do is, well, since we know that no methods are added, why don't we just copy the serial number from the superclass down to this anonymous child class? So we'll just copy that serial number to the child. Now this patch I actually want you to memorize. This is the entire diff to do that, it's 2 lines. So we just say, at the point where we create this anonymous class, copy the serial number from the super down, right? Now if we run this benchmark, the benchmark looks like this. We say the top one is the unpatched Ruby, and the bottom one is our patched Ruby, and we can see that it's about 600 milliseconds faster if we do that copy. And since Ruby can detect every time since Ruby can detect that methods are added, it will automatically increase the serial number for us anyway. So it's totally safe to copy this number between the two. So I'm working on a patch for this. Unfortunately, this is one of those patches where, yes, it works, but you know that it's not the right thing to do. I'm sure you have all done those things. You're like, okay, this works, but I know it's not the right way to do it. So I'm trying to put together the right way to do it. The right way is a few more than 2 lines, unfortunately. But what I want to say here is that failure can lead to success. So you can go through these, when you go through these exercises, you learn more about the systems that you're working with. You can use that knowledge to improve yourself and figure out how you can actually come up with code that does work. So the other thing I want to leave you with is that only optimize code that matters. Measure the code. Don't make the mistake that I did. Measure the code in advance. Make sure that you measure it and find those bottlenecks before you actually try to write optimizations for them. Also, please use more polymorphism. If you use more polymorphism, then it'll make that patch worthwhile. So I would like really appreciate it. That would be very nice. And thank you so much for having me here. It's been an honor. If you have questions about it, I don't know if we have time for questions after this, but later come find me, and I have stickers of my cats, and I promise that I don't bite, so please come say hello to me. Thank you very much.
Thank you, Aaron. Actually, there's some time for Q&A.
Let's do it. Q&A.
There are mics here in the middle of the center of the room, so.
Oh, and you don't have to ask me about inline caches. Oh crap.
Easy one. What's the cost of having the
polymorphic cache in place. I mean, if it only helps a small percentage, that's not necessarily a reason not to do it, but I mean, it has to have some cost if you want to not have a patch in there.
Right, right. So that's a very good question. So the first, I'm actually really glad you brought that up. The first patch that I did, or my first iteration of this patch, actually increased the size of every single call cache site. So I said, all right, let's actually have 2 slots here. And unfortunately, that increased memory a lot. As I pointed out earlier, there's call caches everywhere, so doubling the size of that cache is actually a big deal. The next iteration that I did was essentially a linked list. So each time, if there was a miss, we would actually calculate a new one and add it to the link. Now, the cost at lookup time is essentially the same price as the monomorphic cache. So what it would do is cache the most recently seen at the very first slot. So that one would always be, well, excuse me, it would fill it out to 2. I made it size 2. It would fill it out to 2, and the cost would be approximately the same. Monomorphic call sites were not impacted, and polymorphic call sites were sped up. Now, unfortunately, since I guess that mostly answered. Does that answer your question, Charles? Okay, so just to follow up with that, the main issue is that since the benefit is so small, Koichi was kind of hesitant to add the logic, like, right? Like, the question becomes, for an optimization so tiny, is it worthwhile to maintain this 186-line patch, essentially? Any other questions? Please, ask questions. You don't have to ask about inline caches. It can be about cats or GitHub, because I know everything about it after my 2 weeks employment.
So, is there any problems with just copying the serial for the class into the singleton? I mean, you mentioned there's a 2-line code, but is there any problems with that?
As far as I can tell, no. Since Ruby knows every time a method is added, since it knows that the method is added, it's going to be increasing the serial number of that particular class anyway. So it's saying, okay, I know that you added a method to the singleton object, so let's just increase the serial number of the singleton object. All of that logic exists already. So as far as I can tell, the only reason that it's not doing this today is that if you look at the code that allocates a new class, the code that allocates a new class also increases the serial number. So basically, it's just that allocating a class and increasing the serial number were coupled together. So we need to decouple it.
So I guess if you copy over the serial number and you add a method to that, it's not going to add it to the class above. It's going to add it to that singleton, and that serial number doesn't actually relate to that.
Yes.
Okay.
Yep. Exactly. Anything else? Okay. Thank you very much.